Let's talk about the concept of internal forces diagrams. As we've seen in a prior video, the idea of internal forces are very important because those are the forces that designers use to size or to design the structural elements. Now, in a prior video, we looked at the way that we can identify that shear force, that bending moment, and that normal force at a particular location. The problem is that might not be the location where we might have the maximum moment or the maximum shear. And it will be useful to identify those locations where we have the maximum moment and the maximum shear. Even more, it will be useful to see how this bending moment and this shear changes along the length of an element. And that is the concept of this shear and bending moment diagrams in particular. So let me explain what I mean by that. Let's say that we have an element. Okay, so this is, I want to call it internal force diagrams. And let's say that we have just a beam, simply supported beam. And let's say that we have a distributed force on top of it. I'm gonna do something like this, not along all the top of the element, but I'm just gonna put it from part of the element. So what we can do is, instead of finding the shear bending moment and normal forces at a particular location, let's say at a point like that, what we can do is we can say, let's say that we have some x and y axis. This is going to be my x-axis. This is going to be my y-axis. And what we're going to do is we're going to find an equation of the bending moment as a function of x, and the shear force as a function of x, and the normal forces as a function of x, right? Because now if we plot those equations, or if we maximize those equations by taking the derivative and make it equal to 0, we're able to find some key points for designers to take into consideration in their design. Now, how does this work? It's very similar to what we've seen in the past about finding the internal forces in an element. So the first thing I need to do is to start making a cut. Now, the difference here is we need to cut at every point along the element. And if we were going to cut at every point along the element, the process will take too long. So the key here is to identify that we need to cut every time there is a change in the loading or every time there is a change in the geometry, right? So that is going to be the key point here. So it would be make a cut every time there is a change in loading or geometry. What do I mean by that? Okay, to explain this, let me start with a free body diagram of that element. And I'm going to keep my distributed force as a distributed force for this particular explanation. So at this point, I'm going to have my two support reaction forces. Over here, I'm going to still have my distributed force. And over here, I'm going to have one support reaction force. I'm going to have my x, I'm going to have my y. And we should label all of these forces, but for this explanation, I'm going to leave them without any labels. All right, so I'm going to start making cuts. And the first cut I want to do is, let's say, somewhere over here, okay? And that particular cut is going to help me to define the equation for the shear force and the bending moment between this point over here and this point over here, because my free body diagram is not going to change. Let me show that in a graphical form. So for the red cut, right? So let me change back to red. So So for my red cut, if I choose my left-hand side free body diagram, what we're going to see is the following. I have my reaction forces. I have a little part of my element before the cut. And then what I'm going to see is going to be my internal forces. So I'm going to see my shear force. Remember, my positive shear force by definition is going down, right? So it's going to be my shear. Now this is going to be a function of x, right? It's a function of x. My bending moment, function of x as well. And my normal force, which is also a function of x. One important thing here is that this distance is x. So we can write all of those equations for my shear, for my bending moment, and for my normal force, a function of that distance x. Now my second cut is going to be somewhere, let's try to use green for this one, is going to be somewhere over here, right? The reason for that second cut is now I need to consider that distributed force in the rest of my equation, right? The red cut is only good, my red cut is only good for this distance over here, right? My green cut should be good for the rest of the beam. So I need to create two free body diagrams, do two sets of equations of equilibrium to be able to express that shear force and that bending moment in the whole system, in the whole beam. All right, so for my green cut, what am I gonna see? Okay, let's see. So for my green cut, I'm going to see part of the rest things, the rest of the things that I've seen before. So my support reaction forces on my left hand side. I'm going to see part of the beam that is not loaded, right? And I'm also going to see part of the beam that is loaded with that distributed force, right? Here is my x-axis. Forgot to do my x and y-axis over here. I'm going to make them x-axis, y-axis. Okay. Here's my y-axis. And now I can draw my internal forces. So in this case, it's going to be my shear force. Again, the plan is to make this as a function of x. My bending moment as a function of x. And my normal force as a function of x. This distance from this point to my cut is going to be x, right? Notice that on purpose I've done this diagram with my distributed force because my next step is to be able to do a diagram where I replace that distributed force with an equivalent point load like we've done in the past, and then do my equations of equilibrium and find my bending moment and my normal forces and my shear forces as a function of x. So just to summarize, the idea of these internal force diagrams is to be able to those shear forces and bending moments and those normal forces in the whole length of the structural elements. And one of the key points to be able to do this is to remember to make a cut every time that there is a change in geometry and that there is a change in the loading condition. Before I finish, let me give you another example of where to cut. So let me write here other examples, right? So let's say that I have an element or a structure that will look something like this. And let's say that I have a point load somewhere in here. So for this particular system, I'm going to need 3 cuts. I'm going to need one cut here. That's going to describe those equations for that diagonal element. And in my horizontal element, I'm going to need 2 cuts because there is a change in loading conditions. So I'm going to cut somewhere over here, and I'm going to cut another one over here. So I will need 3 different free body diagrams and 3 different sets of equations of equilibrium to describe the shear force and the bending moment for the whole system. Let's do another example. Let's say now that I have something like this. And let's say that we have a distributed load somewhere in here and a moment. Let's say that we have a moment right there. Yep, I did that all that in red. Let me make the cuts in white. So I'm gonna need 1 cut right here, right before that moment. There's a change in the loading condition. I need another cut over here. There's a change in the loading condition because of that distributed force. So I'm going to need another cut over there. So that one also will need 3 cuts. Let me give you another example. Let's say that now our system might be something like this. Now that particular system, I'm going to need a cut somewhere over here. Then there's a change in the loading condition because of that distributed force, right? I'm going to cut somewhere over here. And then there is a change in the loading condition because of that support. So I'm going to need another cut over here. And after the end of that distributed force, you might need another cut over here, right? So there's going to be 1, 2, 3, 4 cuts for this particular